Okay, today we're going to be continuing in our discussion on chapter 4. And we talked about power functions the last time we were together in section 1. So we're going to continue power functions today, get into compounding interest. We talked about compounding interest the last time, and we talked about how the more often you compound interest in a year, the more money you make. So what is the ultimate? I mean, how many times can you calculate interest? You could do it semi-annually, monthly, weekly, daily. Could I do it hourly? Could I do it every minute? Could I do it every second? Could I do it all the time? Okay. Obviously, the more time you can compound interest in a year, the more money you'll make. And that's what we're going to investigate today and see how that occurs. So we've got quite a few things to do today, and let's get started. First, we're going to fool around a little bit with just a little tiny bit of calculus, okay? This says, what is the limit? That's the abbreviation for limit, as n gets large of 1 plus 1 over n raised to the nth, okay? Everybody able to see that, okay? Okay, so maybe if I turn this light down a little bit, that'll help. All right, so let's let this get large and see what happens. So what I'm going to do is, let's do it for a variety of n's. How about if we do it for n equal to 10, 100, how about 1,000, how about 10,000? I'll punch it into a calculator and see what we get. All right, so if it's 10, it's 1 plus 1/10, which would be 1.1, right? 1 1/10, 1.1 raised to the 10th power, and I get 2.59. So this expression is going to be equal to 2.59, okay? Now, let's do it for 100. 1 plus 100th would be 1.01 raised to the 100th power, and that gives me 2.70. Okay, as we merrily proceed here, let's do 1,000. 1 over 1,000 is 1,000th, so that's 1.001, okay? Raised to the 1,000th power, and I get 2.717. Looks like it's slowing down here a little bit. Let's do 10,000 yet. 1.0001 for 1 and 1/10,000th raised to the 10,000th place gives me 2.718. Okay, so what we're seeing here, no matter how big you go, trust me on this, no matter how big you go, it's just going to get closer and closer and closer to roughly 2.718. It's a number that never stops, decimal number, keeps going on and on forever, kind of like pi, okay? Goes on and on and on forever, never stops, never repeats, but a very good approximation is 2.718. We call that number E. So E is 2.718, roughly, okay? Now, the number E is an amazing number. You are going to find the number E many, many places. You know, pi, we always think about pi in relationship to circles, circumference, and area of circles. But the number E is in banking, it's in radioactive decay, it's in fruit fly colonies. The number E is everywhere, and we're going to get into that more and more and more. So we can use this number E as the base for a power function. Y equals e to the x is a power function like any other power function. It can do vertical and horizontal shifts. So there's a graph of y equals e to the x. Remember, asymptotic to the x-axis, hits here at 1, and then explodes upward, okay? So you can take all of these, and you should be able to describe what's happening. If you put a negative sign in front of the entire function, negative sign, not just on the x, in front of the whole function, all of these red values are positive. And if you put a negative sign in front of it, it's going to flip them all, make them negative. It'll be down here, asymptotic to the x-axis, hit at -1, and then explode downward. How about e to the x plus 2? This curve is e to the x. It stays what it is, e to the x, but now we're going to add 2 to everything. Add 2 to all these red values. Well, if this is 1, it's going to hit up here at 3. It's going to still explode upward, but because it's at 3, it's going to then come down and be asymptotic to the line y equals 2, right? Think about that a second. Y equals e to the minus x, negative x. When you put the negative sign only on the x, instead of shifting it up and down like happened up here, it's going to flip it. It's going to be reflected over here. It'll explode upward, and then it'll go down. Still asymptotic, though, to the positive x-axis. All right, now I've got two things going on here. I've got a -1, and I've got a negative sign in front of the whole thing. Okay? A -1, if you think about a -1, that's going to move this down. It'll hit here. It'll be asymptotic to -1. It'll hit here and explode upward. Okay? But when you put a negative sign here, it's going to flip that. Okay? So a negative sign is going to flip it. So instead of coming like, it's going to come down this way. Okay? Come down here and go down. Instead of being asymptotic to -1, it's going to be asymptotic to +1, okay? So it's kind of a, let me think about that a second. If you have y equals negative e to the x -1, I just want to think about that a second. Yeah, that one's just a little bit trickier than what I had thought. Well, let's take a little more time and think about that one. If you have y equals negative e to the x -1, pull the -1 out, and you get e to the x plus 1, okay? Now, e to the x plus 1, okay, plus 1 would move it up here, hit it 2, explode upward, asymptotic to y equals 1, but a negative sign is going to flip that, make all those positive values negative. So it's going to come down here, go through at -2, be asymptotic to -1, and then explode downward. Okay? That was a little trickier than what I had given it credit for. Okay? All right, so you should be able to move functions around with e to the x in. Okay? Now, let's talk money. From our last class together, here was the formula we talked about. You did quite a few problems in your homework with regards to this formula. Now, this once again is just a touch of calculus. Try to stick with me. Don't copy all this down. I'll talk about what you need here in a minute, but just try to stick with me on this. This is the formula you're familiar with. Now, I claim that this is exactly the same as this. And you might say, what are you talking about? This thing is totally different from that. Well, look up here. I have a power raised to a power, okay? When you have a power raised to a power, don't you multiply the powers? And if you take m over I times in, the i's would cancel and you get mn. So this, let's do it again, a power raised to a power, you take m over I, a power raised to a power, you multiply m over I times in. The i's would cancel and you just get mn. So this is precisely the same as that. Now, what we want to do is what I talked about 5 minutes ago. How often can you compound interest, right? We want to do it semi-annually, that's twice a year, monthly, 12 times, weekly, 52. I want to see how many times we can compound interest, all right? I want to let my m value, the number of times we compound interest, I want to let that explode. I want to let it get really, really super big. So you're compounding interest all the time, okay? So That's what I'm working at here. I want to try to get m to be as big as possible. Now, let's let the letter k equal m over I. If k is m over I can put a k for that m over I. See it? Okay? But what could I do here? I over m. If m over I is k, I over m is the reciprocal of that. Flip it. So I'm going to have to flip for this, I over m. I'd have to flip the k. It's 1 over k. All right? So I have 1 plus 1 over k to the k. Well, we just talked about that. We just talked about that. 1 plus 1 over n raised to the n, right? We just talked about that. And when you have 1 plus 1 over k raised to the k, that is that number e. So in place of this whole mess here, I can put an e. Now let's continue and talk a little bit more about what's going to happen. When m gets big, if m gets big and the bottom of the fraction stays the same, k gets big, okay? So when m gets big, k gets big, so the same thing is happening. As k gets bigger here, it's the same thing as m getting bigger, which means we are trying to figure out what's going to happen to this investment when k or m get as big as you want. You can be compounding interest millions of times in a year, and here is your formula, P naught e to the IN, where I is the interest rate, the annual percentage rate, N is the number of years. I'm going to rewrite it in this formula, which is just a little bit more familiar with calculus. It's P naught e to the KT. That is the formula for compounding interest continuously, all the time. You cannot do better than compounding continuously because you're calculating the interest all the time. Whereas this is the formula when you have a set number of times per year to calculate interest, quarterly, monthly, weekly, whatever. 2 formulas. Make sure you use the correct one in the correct places. Okay, so let's do a problem. $3,500 is compounded continuously for 3 years at 6.25%. Compounded continuously, we know we want to use money, P naught e to the KT. P naught, $3,500. E to the K is your interest rate, is 0.0625, and we're doing it for 3 years, right? Okay, now check your calculator. Check your calculator. You should have an E button. For many of you, it will be on a shift of the ln. Okay, second function or shift. Check your calculator. You should be able to get an e to a power. So let's figure this out. We're going to take 3,500 times. Now, you want to get your e, so do second function or shift of the ln, and that should put an e raised to a power on your calculator, yeah? Okay, and then inside those parentheses, I put 0.0625 times 3. Inside, close the parentheses, and I get 4,221.81. If you invest $3,500 for 3 years at 6.25%, it'll grow to $4,221.81. Look how easy that is, okay? Incredibly easy, compounding continuously. All right, you've got to know which formula to use. All right, next one. Which is better? $5,000 compounded continuously for 2 years at 6%. Well, you could stop, and some of you might be saying, whoa, 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 whoa. I know that compounding continuously is best, so I'm sure that's the better one. Well, let's just continue and keep reading. At 6% or $5,000 monthly at 6.2%. See, I changed the interest rate. If this was 6, yeah, that's better without doing any work, okay? You'll get more money compounded continuously. But I messed with it a little bit. I changed it from 6 to 6.2. We're going to have to work out both of them. I'll do this one first. So I have 5,000 e to the 0.06 times 2, correct? Then for the second one, because we're doing it monthly, it would be $5,000. 1 plus 0.062 divided by, and it's monthly, 12, raised to the 2 times 12. Everybody with me? All right, so the first one is 5,000 times second function ln to get your e raised to a power, and it's 0.12, which is 0.06 times 2. And I get 5637.48. 5637.48. So let's try the monthly one down here. Remember, I always start in the middle. So I got 0.062 divided by 12 equals plus 1 equals raised to the 24th power equals, which is 2 times 12, 24, times 5,000 equals, I get 58.27. Okay? So my playing around with the interest rate, changing it from 0.06 to 0.062, actually made the monthly better for you. You earn more money. Okay? So if everything else is identical, compounded continuously is better, bar none. But you got to be careful when some of the other factors are changed. Okay? All right, next. Diameter of a tree, where T is in years, D of T will give you the diameter in feet. We know the formula is 5.4 over 1 plus 2.9 e to the negative 0.01 t. Okay? All right, find the diameter of a 20-year-old tree. All right, let's do that. So I'm going to put 20 in for t and just crank this out. So it's going to be 5.4 divided by. Now make sure you use parentheses because you're dividing by the whole thing on the bottom. So parenthesis 1 plus 2.9 times. Get your e in there. Second function ln. Okay. Negative 0.01 times 20, and then close your parentheses twice because it's raised to the power, and also you want to enclose the entire bottom. And that gives me 1.6. 20-year-old tree would have 1 6/10 feet for a diameter. You could take that times 12 to see how many inches, and the diameter of a 20-year-old tree would be about 19 inches. Okay? Neat problem, huh? All right. Radioactive iodine decays so that after T days, M of T remains in grams. If you have a substance that's radioactive sitting on the table right in front of you, hopefully you don't, that's pretty dangerous. But there's particles going off into the air, dissipating all the time, and it's like self-destructing. So radioactive iodine does that. We want to know, find the mass when T equals 0 and T equals 20 days. So here's your formula. M of T is equal to 6e to the negative 0.087 T. Okay? So find the mass when T equals 0. Well, that's incredibly easy. When T is 0, this whole thing goes to 0. Anything to the 0 power is 1. So when T equals 0, my mass is just 6. Now, how about when T equals 20? That's a little trickier. 6e to the negative 0.087 times 20. All right, so let's do it. Just crank it in. 6 times. Get your e raised to the power by second function ln. Okay, and I put in negative 0.087 times 20. Close your parentheses, and I get there is 1.053 grams remaining. You see, it's dissipated. Okay, and in only 20 days, it's down that far. Okay? You might say, well, that's a great thing to do with radioactive waste from a nuclear power plant. Just let it sit around, then it'll just go away. Yeah, but all those particles go into you and into me, causing cancer and all other kinds of horrendous problems. Okay, that is E. Should be able to do problems with E involved. You should be able to move graphs around. So on here I've got one of the problems from chapter 3. I know we're getting to the end of our course and we're going to have a final, so I want to remind you occasionally of problems. Get your possible zeros, check which ones are actually zeros by synthetic division and sketch it. And here are some problems using the formula we got, P naught e to the kt, and so on. Okay, I don't think that you're going to find this to be too difficult.